Yes, welcome to the next session, probably the last session of the coordination compounds, in which, see, in the last class I explained in detail the stereoisomerism and the valence bond theory of a few complexes with the coordination number 4 with sp3 hybridization like NiCO4 times and that is tetrahedral complex, dsp2 hybridization, that is square planar, NiCN4 times 2 minus, even cuprammonium ion also CuNH3 4 times will have dsp2 hybridization. Then where the coordination number is 6, it is octahedral. In this I think I explained D2sp3 hybridization. If not, I will take up that now. So today I am going to take up valence bond theory of some more complex compounds. After that, the crystal field theory, then stability of the complexes and the colors exhibited by the complexes. Yes, let's start with the valence bond theory. Consider CO NH3 6 times Cl3 or CO NH3 6 times 3 plus. Here the oxidation state of cobalt is +3 and cobalt has got the atomic number of 27. It is 3d7 and 4s2. Of course argon. +3 state is 3d6 and 4s0. Sorry, 3d6 and 4s0. So CO3 plus present in CONH3 6 times Cl3 or CONH3 6 times 3 plus, that is hexammine cobalt 3 chloride. Cobalt is in +3 state, so its electronic configuration is 3d6 4s0. So I will write 3d6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. This is 3d6. There are 4 unpaired electrons and then you have 4s, that is 0, and 4p, that is 0. 4p, sorry, 4p, that is 0. In this complex, ammonia is the ligand. It's a strong ligand. When this ammonia ligand approaches cobalt, the cobalt ion behaves in a peculiar manner against Hund's rule of maximum multiplicity. The 4 unpaired electrons get paired up. 1 pair, 2 pairs and 3 pairs. 3d6. 2 vacant orbitals are there. New 2 vacant orbitals are formed at the 3d level. There are 6 ammonia ligands, 6 ammonia ligands are giving 6 into 2, 12 electrons or 6 pair of electrons. The 6 pairs are accommodated in the 6 vacant orbitals, but these are of different energy, but 12 electrons are of same energy. Therefore, after 3d6, this is 3d6, the vacant orbitals, the vacant orbitals, 6 vacant orbitals join to form a single hybridized orbital. For this, the contribution is 2 from D, 1 from S and 3 from P. It is D2sp3 hybridization, and the 12 electrons are accommodated here. There is no difference in the electrons, but I am writing just to show that these electrons have come from the ligand. So 1, 2, 3, 4, 5, 6, 12 electrons, 6 pairs or 12 electrons have come from the 6 ammonia ligands or amine. The ligand name is amine. 12 electrons. It forms D2sp3 hybridization, and the shape of this is octahedral shape. Since there is no unpaired electron, the magnetic moment is equal to 0 because the unpaired electron is equal to 0. It is diamagnetic. So this is about CO NH3 6 times Cl3. Here we shall consider one more complex of cobalt, COF6 3 plus. COF6 3 plus. COF6 should be 3 minus, it should be F ligand, it should be CO minus 6 is equal to minus 3. Therefore, CO is equal to 6 minus 3 is equal to plus 3. Therefore, it should be minus 3. CO F6 minus 3. Consider another complex of cobalt where fluorido is the ligand. Again, it is in plus 3 state. Therefore, electronic configuration same as that of the previous one, 3d6, 4s0, 4p0, 3d6, 4s0, 4p0. Fine, I will write it. 3d6, 1, 2, 3, 4, all of them have spin of plus 1. So this will be, and this will. So this is 4 unpaired electrons are there. 1 paired electron and 4 unpaired electrons. You have 4s and 4p vacant. Fluorido is not a strong ligand as Cn minus, EDTA, NH3, etc. It's a weak ligand. Therefore, it follows Hund's multiplicity rule. It hasn't got the capacity to make the unpaired electrons to get paired. The reason not explained here can be explained in the next theory, crystal field theory. Okay, so F has no capacity to make these 4 unpaired electrons to pair up, but F6 is providing 12 electrons. These 12 electrons must be accommodated in 6 orbitals of equal energy. Now only 4 vacant orbitals are available. Therefore, it will go for the next d orbital. This is 4d, this is 4s, this is 4p, this is d. So 1 from s, 3 from p, and 2 will be got from, this is number 5 and 6. So I will write it again. So this is 5 and 6. These vacant orbitals hybridize, resulting in the formation of, so 3d6 already there, a new hybridization will take place with 4d. One orbital from 4s, 3 from 4p, and 2 from 4d. The 6 vacant orbitals are provided here, and this is sp3d2. Going back to CONH3, it is d2sp3. 3d is used up, pairing will take place, whereas here pairing will not take place. 3d6 will remain as 3d6. So it will borrow 2 orbitals from 4d, sp3d2. Instead of d2sp3, it forms sp3d2. This is also octahedral. So if the octahedral, where the coordination number is 6, and if the ligand is weak, it goes according to Hund's multiplicity rule, and it borrows orbital from the outer shell, outer suborbital, that is 4d, forming sp3d2, not d2sp3. So 12 electrons are accommodated here. 12 electrons are given by the 6 fluoride ligands. They are accommodated here. sp3d2. So octahedral shape, coordination number 6, hybridization 6 orbitals combine, but the difference is here inner d is used up, here outer d is used up. Therefore this is called the inner complex, and that's called the outer complex. So this is called the outer complex, and this is called the inner complex. So if the ligand is strong, CO, cobalt, similarly we can apply it to others, shows the inner complex formation where mu is equal to 0, diamagnetic. If it is weak ligand, then it is paramagnetic and it forms outer complex. So this is how we explain the valence bond theory to different complexes or different complex ions. Now we shall pass on to the next theory, that is crystal field theory. Crystal field theory. See, in the valence bond theory, sometimes the unpaired electrons get paired up against Hund's multiplicity rule. Sometimes no. For that we said strong ligand and weak ligands. Strong and weak ligands. There are many exceptions to this. For example, in the case of cuprammonium sulfate, one electron will be left over in 3D and that should be transferred. An exception which cannot be explained by VBT, but it can be explained by the crystal field theory. According to this theory, the bond between the metal and the ligand is electrostatic or it is ionic in nature. Metal and the ligand, the attraction, the bond is electrostatic in nature. Here, the ionic ligands as considered as point charges. Important. The ionic ligands are considered as point charges, whereas the neutral ones or the neutral ligands behave like dipoles. Two things to be remembered. Ionic ligands behave like point charges, whereas neutral ones behave like dipoles. Yes, with this we shall go to more details of the crystal field theory. You know that in the d orbital, d subshell, we have 5 orbitals which are called dxy, dyz, dzx, dx square minus y square and dz square. All these are of same energy. They are all of same energy. It's called degenerate d orbital. D orbital is degenerate. Degenerate. They are all of equal energy. But when the ligands approach this degenerate d orbital, the ligands have got lone pair. They have got lone pair. If they are symmetrical, okay, no problem, degeneracy will be maintained. Unsymmetrical, then the ligand has got the lone pair. There will be repulsion between the lone pair and the electrons present in the d subshell. Okay. Now, due to this repulsion etc., the degeneracy in the d orbital is lost. So this is d orbital. This d orbital in presence of in the case of octahedral complexes and in the case of tetrahedral complexes, the degeneracy is lost and then it is split into two energy levels. Now you consider an octahedral complex, two energy levels, one with the lower energy, one with a higher energy. Which are they? The first and the second and third, xd, xy, yz and zx is of lower energy, while 4 and 5, that is d x square minus y square and d z square, will be of higher energy. This is the average energy. This type of splitting of the d orbital into two levels where degeneracy is lost is called crystal field splitting. Crystal field splitting. The energy required for this, the difference in energy between the two levels is called delta zero. O stands for octahedral. Delta is energy. This is the average energy. The two x square minus y square, its energy is increased by 5 by 3, that is 0.6 increased than the normal, whereas these three will be decreased by 2 by 5, that is minus 0.4, minus 0. So x square minus y square and z square will have higher energy, and xy, yz and zx will have lower energy. This splitting, as I said, is called crystal field splitting, and the difference in energy is called crystal field splitting energy. How far it will be split? What will be delta zero value? It depends upon the nature of the ligand. If the ligand is strong, splitting will be more, delta zero will be higher. If the ligand is weak, splitting will be less, delta zero will be less. So it depends upon the ligand, it depends upon the nature of the metal ion also. Why x square minus y square and z square will have higher energy? Because when the ligand approaches, it will come in the same line as that of d x square minus y square and d z square. Therefore, there will be repulsion between the electrons of the ligand and d x square minus y square and z square. Due to this repulsion between the electrons, it will have the higher energy, it will be split to have the higher energy. Okay, fine. Then how do you explain the formation of complexes? How do you explain the magnetic behavior of this crystal according to crystal field theory? Now let us say in the central metal atom, we have only one electron, D1. This D1 will be filled into X, Y. Okay, fine. D2, yes, to the second one. If there are 3 electrons, D3, fine. XY, YZ, ZX are filled up. No problem whatsoever. Suppose the 4th electron is there in the D subshell. Then it has 2 options. The 4th electron, D4, 4th electron can go to DXY to form pairing, or it may go to the higher level dx square minus y square having 4 unpaired electrons. 2 chances are there. So I will write them again. So dx square minus y square, dz square, and xy, yz. This is T2G level and this is EG level, Gerard, German. So this is the splitting. 1 electron here, 1 electron here, 1 electron, D3 over. For D4, as I said, 2 chances are there. Now it may be like this. So D1 is in XY, D2 is in YZ, D3 is in ZX, D4 is also added on to XY. There will be pairing. Or it may go to this level, EG. The 4th electron can occupy lower energy or can occupy EG, that is dx square minus y square. The question is, will it be paired or will it be unpaired? Goes to that. It depends upon 2 factors. One, difference in the energy, that is delta 0. Another is called the pairing energy. If 2 electrons are to be paired, they have to overcome the repulsive force. There will be strong repulsion. It has to overcome that. So it will have some energy. There are 2 types of energy now. Delta 0, the splitting energy, and the pairing energy. Pairing energy. If the pairing energy is less, I will call it PE. If pairing energy is less than delta 0, then the pairing will take place. Pairing will take place. When a pairing takes place, number of unpaired electrons decrease. When the number of unpaired electrons decrease, N, the unpaired electrons decrease. When it decreases, mu will also decrease. Lower magnetic moment, spin only magnetic moment. If this is the case, mu will decrease. Under what? It will form low spin complexes. So low spin, because there were 3 unpaired electrons, now it has become 2 unpaired electrons. So it will form low spin complex. This pairing will take place if the ligand is strong. See here? This was not explained by valence bond theory. Here it's explaining how the pairing will take place. due to the losing of the degeneracy in the d orbital. Okay, if delta 0 is less than pairing energy, then the electron goes to the next level. Now you have 4 unpaired electrons. See here, when pairing takes place, number of unpaired electrons decrease. When it is excited, goes to the EG level, number of unpaired electrons increase. This is called high spin complex. This is called low spin complex. This is called high spin complex. Low spin complex is formed when the ligand is very strong. When the ligand is weak, the splitting will be less. Delta 0 will be less than the pairing energy. Therefore, this. The next electron, again, that depends upon the nature of the ligand, may be there or it may be here. Still less. Low spin is formed. So, the crystal field theory explains the losing of degeneracy in the d orbital and how exactly the electrons are filled into the d subshell. Will up to 1, 2, 3, no problem, x, y, y, z, zx each will have 1 electron. The problem arises with the 4th electron. Will it be paired or will it go to the higher level? That depends upon the nature of the ligand and the pairing energy and delta naught. If the pairing energy is less, the pairing will take place, low spin complexes are formed. If delta 0 is less than that, it goes to the next, high spin complexes are formed. So this is in the case of octahedral complexes. In the case of tetrahedral complexes, the approach of the ligand is in terms of xy, yz, zx. Therefore, xy, yz and zx will have higher energy. X square, y square, x square minus y square and z square d will have lower energy. D, xy, yz and zx will have higher energy. Exactly, it is reversed. But here the splitting energy, which is called delta t, small t, sorry, tetrahedral. This is for tetrahedral. Delta t. This delta t is found to be 4/9. The splitting is very crystal field splitting energy is very less, and it is found to be 4/9, not even 50% of delta 0. That means it will form easily the high spin complexes. So this is about crystal field theory. The crystal field theory, the splitting etc. will depend upon the ligands, whether it is the strong ligand or the weak ligand etc. At the same time, if it is the element is in the 4D, see, if the metal belongs to 3D, okay. If it belongs to 4D, delta naught, in the case of octahedral complexes, for 4D, delta V naught will be 50% more than 3D. That means splitting is more and more. Splitting energy, crystal field splitting energy in the case of 4D is more than that of 3D. It is almost 50% more. That means pairing will be easier. Low spin complexes are easier there. And then if the oxidation state is less, then delta 0 will be less. If the oxidation state, for example Cr2, will have lesser delta 0 than Cr3 plus, this is higher. It depends upon the charge, it depends upon the oxidation state of the central metal. So this is about the crystal field theory. The crystal field theory explains why pairing will take place in some of them, where n number of unpaired electrons decrease and mu decreases, and why pairing will not take place, why it forms n unpaired electrons increase and mu will increase. So it will clearly explain the paramagnetic and the diamagnetic behavior. Crystal field theory. Okay, we can actually calculate the energy of each of them. We shall not go into those details. Then we'll come to the stability. Suppose we have a coordination compound where metal combines with 4 ligands. Its coordination number is 4. Then the ligands attach to metal one by one. Let us say M plus L gives rise to Ml. Here there is association of metal with the ligand. Therefore, it is association energy or stability, the energy involved in the stability. It's called stability constant. I will call it K1. K1 is equal to, according to law of mass action, Ml divided by M into L. I will call it K1. Next, Ml will combine again with L, resulting in the formation of Ml2. Then K2 is equal to active mass of Ml2 by active mass of Ml into active mass of L. Next, Ml2 will combine with L, resulting in the formation of Ml3. Therefore, K3 is equal to active mass of Ml3 by active mass of Ml2 into active mass of L. And the last stage, because its coordination number is 4, Ml3 plus L gives rise to Ml4. Here K4 is equal to active mass of Ml4 divided by active mass of Ml3 into active mass of L. The stability constant for the whole system, that is M plus 4L, gives rise to Ml4. I will call it K. K is equal to K1 into K2 into K3 into K4. If there are n number of ligands, suppose it is M, L, n number of ligands are there, then it will be Kn is equal to K1 into K2 up to Kn. If the stability constant is more and more, the stability of the coordination compound will be more and more. This is association. So in the case of acids, we call dissociation constant. In the case of bases, we call dissociation constant. If the dissociation constant is more and more, molecule present will be less and less. Whereas this one is association constant. Stability constant is nothing but association constant, because metal is associating itself with the ligand. If the association constant is more and more, stability of the coordination compound is more and more. So, the stability constant, or we can call it association constant, decides the stability of the coordination compound. It is exactly opposite to the dissociation constant of an electrolyte. If it is for acids, it is Ka. If it is for base, it is Kb. So this decides the stability. The energy will decide the stability. The stability constant will decide the stability of it. If this value of K is more and more, the compound is more and more stable. This is called the stability constant or stability of the complexes. And the last part left over is colors of coordination compounds. Now you consider sodium, potassium, lithium, etc. Or you consider beryllium, magnesium, then calcium, etc. Their compounds: sodium chloride, sodium nitrate, sodium sulfate, sodium phosphate, potassium chloride, potassium nitrate, potassium sulfate, potassium phosphate. Similarly, magnesium chloride, magnesium sulfate, all these are colorless. Whereas you consider transition metals, their ions. See, iron, ferrous sulfate is light green in color. Ferric chloride or ferric sulfate is brown. This is light green. Copper ion is blue in color. Manganese, a transition metal, Mn+7 is purple. Ml+6 is green. This is purple. This is green. +4 is brown. +2 is light pink in color. So, transition metal ions exhibit colors, and you already know that alkali metals like lithium, sodium, potassium, or alkaline earth metals, beryllium, magnesium, there may be exceptions here and there. Very 1 or 2 exceptions may be there out of 1000 or 10,000. Calcium, strontium, barium, etc. They do not form coordination compounds, do not form complexes, or do not form coordination compound. Do not form coordination compounds because they have no capacity to accept the electrons from the ligands. Whereas transition metals, K4FeCN6 is a complex. Iron is transition metal. CONH3 6 times Cl3. CO is a transition metal. NiCO 4 times. Ni is a transition metal. CuNH3 4 times SO4. Cu is a transition metal. Fe4, FeCN6 thrice, ferric ferrocyanide Prussian blue is iron transition, and you know that here and there may be exceptions, they are all colored. The central metal ion is responsible for giving the color, and it depends upon the nature of the ligand. If a particular metal has ammonia as the ligand, its color is different. If cyanide is the ligand, the color is different. So it depends upon the ligand also. First of all, why a particular ion, a particular compound is colored? See, benzene is colorless. I will sum up this color in another 2 or 3 minutes. Benzene is colorless. If you heat it with nitric acid and sulfuric acid mixture, it forms nitrobenzene. This nitrobenzene is yellow in color. Why it is yellow in color? Benzene absorbs light in the visible ultraviolet region of the spectra, whereas nitrobenzene absorbs light in the visible region of the spectra, that is from 400 nanometer to 700 nanometer. So, if a substance is to be colored, it should absorb light in the visible region of the spectra, that is from 400 nanometer to 700 nanometer. Main thing. What happens with this visible light? So 400 to 700, not a very strong, this wavelength, not very strong energy. This is sufficient for DD transition of electrons. DD transition of electrons, that is from T to G to EG, or in the case of tetrahedral complexes, it is the reverse. So this is DD transition. For this DD transition, 400 to 700 nanometer is sufficient for it. Hence, it is colored. One more thing you should know here is, if one color, let us say color A in the Vidgaya region from violet to red, if color A is absorbed, the electron gets excited, it comes back. While coming back, it transmits the energy and it gives the complementary color. Complementary color. So if it absorbs one light, the coordination compound will appear its complementary color. Okay, I'll give you this with an example. CO F6 3 minus absorbs energy in the 700 nanometer region, that is the red light region. It appears green or maybe slightly bluish green, whereas CO with C2O4 thrice oxalato, this is fluorido, this is oxalato, the absorption band shifts to the lower one, 600. It absorbs yellow light, this is absorption, this is emission, transmission. Yellow, it appears dark green, complementary color. In the case of CO, En thrice, 3 plus, this is also 3 plus. CO, En thrice, En is a very strong ligand, shifts to the lower wavelength side 470, and that is the blue region. It appears yellowish orange. The complementary color is seen. So, coordination compounds absorb energy in the visible region of the spectra 700 to 400 nanometer, or reverse, 400 to 700 nanometer. If it absorbs one color, electron get excited, while coming back it transmits the complementary color. I have given you the absorption band here, 700, 600, 470, and the color that is absorbed and the color that is transmitted. So this is how you can calculate actually the energy required for this excitation of electron by any particular light. So this is about the coordination compound. I will tell you, I started with, not in this class, in the first class, coordination. What are the types of salts we have? And then the terms and terminologies that are used in coordination compounds. After that, we came to the ligands, different types of ligands, classification of ligands. Then came Werner's theory of coordination compounds. After that, classification of the complexes into cationic complexes, anionic complexes, neutral complexes, then coordinate complexes, etc., and their examples. How to write the formula of coordination compounds, how to write the IUPAC names of these coordination compounds. Then after that, slowly we switched on to the isomerism, structural and stereoisomerism. After that, the theories to explain the formation of coordination compounds, the two theories, valence bond theory and crystal field theory. After that, I explained stability of the coordination compounds and the colors of the coordination compounds. This ends up the chapter coordination compounds. I thank you very much for having joined the sessions, the 5 sessions. Now you get access to the class practice packs sent by me and answer with a passport. Thank you very much.